We talked about quantum numbers quite a bit, so now we're going to start talking about the energy levels for atoms, particularly multi-electron atoms, and how quantum numbers are related to that. First, we're going to discuss the energy levels of a hydrogen atom. Next, we're going to talk about the energy levels of multi-electron atoms. We're going to talk about how that's different from the hydrogen atom due to penetration and shielding. Very importantly, we're going to talk about effective nuclear charge, and this will be a really important concept for when we start talking about periodic trends. We're also going to talk about Hund's rule and the Aufbau Principle. Okay, so last time we talked about how the Schrödinger equation can be used to solve for all of the wave functions for all the different energy states for the hydrogen atom. And we talked about how the principal quantum number, well, we used quantum numbers to describe the wave functions. And the principal quantum number told us the energy state. So it told us the number of nodes, n-1. And that should lead us to believe that all orbitals with the same principal quantum number, or n, should have the same energy. And for the hydrogen atom, that's true. So for the hydrogen atom, a 1s orbital is lower in energy than the 2s, but the 2s and 2p are what we call degenerate, meaning they have the same energy level. And the 3s, 3p, and 3d sublevel are also degenerate. They all have the same energy level. However, this is not true for a multi-electron atom. What you've probably been familiar with from high school, if you took chemistry in high school, is the order is 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. You're probably familiar with that. But the reason why these energy states are now different has to do with penetration and shielding. So the factors that affect the atomic orbital energies are the nuclear charge and the shielding by other electrons. So the higher your nuclear charge, or the closer your electrons are to the nucleus, the lower the sublevel energy. And if there are electrons shielding other electrons, then that will reduce the full nuclear charge to an effective nuclear charge, or a Z effective. So the effective nuclear charge is the charge that the electron actually experiences. And so this will be very dependent upon how many electrons are shielding these outer electrons from the nuclear charge. Orbital shape also has an important impact on sublevel energy. And we're going to talk about why this is in a second. So this is just a picture of penetration and shielding. Well, really just shielding. So here we have an electron of interest, and we have this positively charged nucleus. And electrons that are between this electron that we care about and this nucleus are going to shield the nucleus, and so this electron won't feel as great of a charge. And the more angular nodes that you have for an orbital, the worse you are at shielding. So an s orbital is much better at shielding than, say, a p. P is better at shielding than a d or an f orbital. So each energy level is split into sublevels of differing energy, and this splitting is caused by penetration, just like we mentioned. So if you have for a given n value, so say we have a principal quantum number of 4, the lower your L value, the lower in energy your sublevel is going to be. So a 4s is lower in energy than a 4p, which is lower in energy than a 4d, which is lower in energy than a 4f. So this is the actual order of energy levels. 1s is lowest in energy, it's closest to the nucleus. This is for a multi-electron atom, then 2s, then 2p, then 3s, 3p, 3d. Now 4s is actually lower in energy than our 3d, and that's because, and these kind of flip back and forth, and we'll talk about this later. So I also wanted to talk about what an electron configuration is in an orbital diagram, and I'm going to draw some for you in a minute. But electron configuration, we use this notation where we put our principal quantum number, then the name of the orbital as in S, P, D, or F, so that's represented by L, and then the number of electrons in the sublevel. And if we're doing an orbital diagram, you can do it a couple different ways. Some people use a box to indicate each orbital. Some people use a circle. I personally just use a line, and the reason why I do this is because it's fast, honestly. The last thing we need to talk about before we do electron configurations and orbital diagrams is the Aufbau Principle and Hund's rule. So the Aufbau Principle is just the building up principle. It says that electrons want to be in the most stable electron configuration. So it's most stable for electrons to be occupied in these lower energy orbitals first. So electrons will fill the lowest energy orbitals first and then build up into higher energy levels. So if we were to say that there were 2 electrons in our atom, we would simply fill up our orbital and say that we have 2 electrons in our 1s orbital, or we have a 1s2 electron configuration. Say we had 8 electrons, such as oxygen, we would fill these first 2 in our 1s orbital, and then we would go to 2s. And then when we get to the 2p, we follow Hund's rule. Hund's rule is the rule of the school bus. It just says that if you have orbitals of the same energy available, electrons will spread out before they pair up. So this is our orbital diagram for oxygen. Hund's rule is the rule of the school bus, which says that when orbitals of equal energy are available, electrons will spread out before they pair up. This will give the lowest energy electron configuration. We call this the rule of the school bus because if you go on a school bus or the light rail or a regular city bus, typically people will spread out into different seats before they start pairing up. And I had a male colleague say it's also the rule of the urinal. So however you want to think about that, people aren't going to go to the urinal that's already occupied. They're going to go to the one that's empty. And this has to do with electron-electron repulsion. Electrons want to be spread out as far away from each other as they can.